welcome to today's presentation. My name is Pat Martens, and I work as a consultant for a company called Bridge Preservation and Inspection Services. I'm out of Jefferson City, Missouri. Today's training is designed to be a thorough look at the hydrodemolition process and things to be aware of with the technology, along with some things to look for in the field for evaluating hydrodemolition surface cutting. I'm going to ask you to hold your questions, I think, until the end of the presentation session, but you can also put questions in the chat box if you like. And then sometimes I noticed on these Teams presentations, the slide transition can have a little bit of a delay. So kind of bear with me on that. I'll kind of try to work through that as best I can. I hope it doesn't get off too far. All right, hope everybody's seeing that. So the presentation outline for today, it's pretty short actually. I just want to start off with a look at the equipment and the theory behind the technology. Usually when I do these trainings, I try to overview the generic fast track process. And I'm going to do that today with and kind of tie it closely together with your North Carolina DOT specification as I do that. And then as I get through that, I have some examples of some hydrodemolition work done in the field. I wanted to kind of go through some of those for you and kind of help you out with some tips, things to look for out in the field. So as I start out here, I thought it would be interesting to show a few pictures from some older jobs in North Carolina, actually. Some of you may be familiar with these. I only have a few. This first set here is out of Plymouth County, and I believe it was done in about 2005, probably one of the earlier ones done in North Carolina. And looking at this one, looks like a pretty rough deck, so kind of curious how this one's holding up after 15 years. Hopefully it's still performing. Looks like some of the milling equipment kind of on the adjacent slide there in operation. Second slide here is the same location. You see the hydrodemolition robot at work. And then some of the finished cleaned up surface after the hydroing was completed. And then a little more work actually still going on in the background in that right slide there. I think the rest of these I have here are out of Haywood County, I want to say, about 2009 time period or so. So a little over 10 years. Top left there, surface has had some scarification on it. Looks like some patches visible in the deck. Lots of rebar exposure showing up, several patches in there. It looks like a fairly deteriorated deck there. Another look at a robot working, just kind of the mist cloud there from the operation, and some more results showing the deterioration of the deck. Looks like where the rebar is not exposed, there are patches in place. So again, you can tell it's been a pretty rough deck to have to work on. So that's just a few slides. It's kind of a little primer there to get us going, show some of the early work done in North Carolina. Hydrodemolition equipment is really pretty basic. It's a mechanical process that utilizes high pressure water for concrete removal. So this is just a real crude schematic of what takes place. You have a water source, it's fed into the pumping units, which pressurizes and sends a high pressure stream out to the robot. This here's an animated view of that process inside the trailer where the power unit and the pumps are stored. You can see how the water is coming into the system, kind of there from on the right side, and then it runs through and is pumped back out to the robot. And that robot is the feature attraction for the hydrodemolition operation. It's going to do all the work for us. Not sure how many of you have seen this particular unit or one like it. It's a self-propelled, fully programmable unit. This one here is manufactured by a company called Conjet, and they're based in Sweden. They're one of the leading manufacturers of hydrodemolition equipment in the world. Many of the newer units you'll find out there, they run on wireless technology nowadays, and even the older units kind of run with remote control systems. Here's another type of robot. In the foreground, if you look at this one in particular, you see a short platform on the front of the unit. This would be where the operator would access his control panel. If you've not seen hydrodemolition robots before, what you find then is that the cutting mechanism is actually on the back end of the robot. So if you're looking at this picture, the machine is moving from right to left, and you can see the debris trail in the background. So that water jet would be housed within the skirted area that you see on the back side of the machine. And there's that draping that runs around the end there to help prevent debris from flying out, to help protect the workers' traffic. If you're working with adjacent traffic, the contractor may need to supplement his work zone with some additional protection. Just depends on the quality of that skirting and how well it's able to contain all of the material within that base there. A little bit different look here. You get a look at the guts, so to speak, inside the unit. There's a slide track, and that's the jet assembly inside that you're seeing. It'll slide back and forth on that track. And then if you tilt the machine up, you can see the very bottom. Now you're looking at the very bottom of the machine, and this is where you'll see the jet itself. And what you see is that there's like a covering coming out that the orifice is housed just inside of that casing there and that covering. So if we take away that shell, you see how the inside is working. It's just kind of a different view of the jet assembly, and there's that track that kind of runs perpendicular or transversely there, and that's what that jet assembly is going to run back and forth on, is that particular track there. Now your jet nozzle will be down near the concrete surface, and it's going to be a tight 0-degree stream that you're emitting out into that concrete, or at least that's what your objective is. You want something as close to 0 degrees as possible, especially when you're using your impact cutting type jet. So that stream, what it's going to do then is it's going to attack the concrete. For high production type equipment, you'll find that the jet will have kind of a pulsation that takes place with it, and also some oscillation or different toggling that'll allow the jet to operate at different angles and attack the concrete in different manners. So what you see here, this is the kind of the dynamics of the jet stream. So it comes out in a very narrow path, and what you'll find with these jets is there's an effective core length that holds together for a short distance. That would be the little bit darker shading that you're seeing here of that solid blue. You'll see this. It's kind of on that left side coming out of the jet is where that jet is located on the left. So you're seeing that little bit darker blue area there. That's going to be your core of that jet. And then the remainder of that jet, or the outside portion of that jet, is going to kind of disperse. So the longer you can hold that jet together, the longer that effective length will be able to attack the surface of the concrete that you're working on. So this would be a look at the unobstructed view, I guess, of that jet and how it's dispersing. You can kind of see how it's fairly tight, and then over length it starts to kind of fall apart. Then a closer look at the nozzle assembly itself. That blue housing it covers the orifices, which would be kind of that gold piece that slides into the actual nozzle, and that's where the stream's going to be forced out of that orifice there. This would be an actual nozzle. For hydrodemolition operations, it's generally going to be a 0-degree stream because you want the high pressure through a very tight jet stream. And then depending on the desired type of cut, it can dictate the nozzle type and actions that's desired on the machinery. This is a different type of jet. This is what we call spin jet. And you'll notice there's 2 orifices kind of on the base of it there. The jet will actually spin. And these spin jets are generally more for cleaning and scarification type work. You may see them with ultra high pressure blasting equipment in particular. For true hydrodemolition cutting, what you want is a pulsating direct impact with a single 0-degree jet stream. That's kind of the aim there. So I want to bring this all together then into the theory of the process. One is, how does hydrodemolition work to do what we want it to do? But then second, how does the relationship between the water pressure, the flow rate, and selectivity all work together in the process? And hopefully when you see this, it will help you understand better in the field what it is you're truly trying to do and why certain equipment does matter and makes a difference out there. Just depends on what the job scope is. So when you think of the term hydrodemolition, you probably think concrete removal. And yes, hydrodemolition equipment is ideal for concrete removal, and not just on poor concrete. But the equipment, it can be used to remove sound or unsound concrete to really about any depth. It's just a matter of how much exposure time the high pressure water jet has on the concrete specimen. So if you have been around the technology, you also probably understand how it gives an ideal surface preparation too. That's what's key to what we're doing with overlay construction, because bond is critical, and an enhanced surface prep gives a better bondable surface for us. So it leaves a very roughened texture, and that helps make it valuable as a restoration tool, and that's why it's so effective in bridge deck overlay construction. So how does Hydro work? Well, there's three things that are essentially happening. First of all, you think about just the impact that the water jet of, say, 14, 15,000 PSI can deliver to the concrete when it hits it. And some units are actually going to work upwards of 35 to 40,000 PSI, so that's a lot of force. When you're in these pressure ranges, the impact can break up deteriorated or weakened concrete fairly easily. Second, there is a pressurization of cracks and microfractures that exist within the concrete surface. So as the water is delivered at high pressure, it's also filling cavities and cracks and crevices in the surface. And in doing so, it's pressurizing and breaking up or blowing apart those areas within the surface. And then thirdly, when you consider these units can generate 65, 70 gallons per minute and more of water consumption, just think about how much that water can create a rapid erosion effect, in which the fines within the concrete mix are being washed out and exposing the aggregate. That helps to develop that very roughened surface texture as that coarse aggregate is left in place, protruding and leaving more surface area for us to bond to. So that rapid erosion is what's given us that great profile that we desire out of the process. Got a few terms here. First one I refer to as fast track hydrodemolition. May also be referred to as total surface selective removal hydrodemolition. Some states refer to it as non-rebar exposure type hydrodemolition. This is essentially what I would say your specification is using. The fast track process, what it is, it's really a type of cut with the robot. So it's generally going to be a fairly shallow cut depending on the concrete quality. With this type of cut, what we do is we calibrate a water jet in a single pass, such that the equipment will selectively remove all the deteriorated or weakened concrete in the surface, and then at the same time provide the roughened surface that's desirable for the attachment of the overlay. So the key to the process is in that term I mentioned called selective removal. It's defined as the capacity to completely eliminate all weakened or deteriorated concrete below a certain level of jet resistance. So what's key to it is that it can do this regardless of the depth of the defect that we have. So the important part about this is that not all equipment's going to be able to do this. It takes certain parameters of the equipment to cut in this particular manner. So with this method, we are cutting out all the bad concrete, saving as much of the sound concrete as we can. And that is your concept of selective removal. So it's the key concept for what you're doing on your bridge deck preparation ahead of your overlay. But it does take a calibrated technique to do it correctly. If you can envision here, concrete does not deteriorate at a uniform rate. the depth of the fracture plane within the concrete will vary throughout the slab. So with the fast track process, we're essentially trying to calibrate the machine such that we can, as closely as possible, trace that fracture line or just slightly below it. So you may be thinking, okay, how can you cut variably like that? The reason is, at the right calibration, the jet is not being resisted until it's done so by the higher strength concrete. So let's zero in a bit more on this selective removal and the factors affecting it. It's important to understand how the relationship between water pressure and selective removal relates to each other. It would seem logical that if you're cutting at a certain pressure range, to cut out concrete, that more pressure would have to be better. But that's not really true for selective removal. And here's why. There's a target zone where pressure most effectively will selectively remove concrete. So as you can see from this graph, and this is put out by Conjet, the equipment manufacturer, that for most 4,000 PSI concrete, that pressure range is going to fall somewhere between around a 14 to 18,000 PSI range, or about they generally figure about 3.5 times the nominal concrete strength. So that value is going to kind of slide depending on the quality of your concrete. Of course, if you have poorer concretes, that pressure range is probably going to be nearer to 14 to 15,000 PSI, whereas if you have good high quality concretes, it may be up closer to that 16, 17,000 plus range.
That's right.
So this kind of shows you the difference between pressure ranges and how the jet is trying to cut. The darker gray area in the pictures here, that's the area of sound concrete. So consider the red and the yellow lines as different removal depths based on varying pressure at similar jet exposure times at the surface. So in our left picture, that's the removal depth generally being followed by the quality level of the concrete in a range of around 13 to 17,000 PSI. And then notice how the lines are trying to follow that general fracture of the concrete. This is where the jet is encountering that resistance. So the red line is going to be a lower pressure, while the yellow line will be a higher pressure for an equivalent speed of the jet. And then that jet is not being resisted by the substrate until it gets to the sound concrete based on its strength. So you see that the red line is not quite getting down all the way through the fracture into that dark gray zone. Now the yellow line does get completely below, and that is where you want to be. And the calibration process is what you use to try to get to that key point and find that zone of cutting that you're looking for. Now look on the right side. This is where a higher pressure is being used. So you see how the line is much more uniform in its projected cut. So what's happening here is, due to the much higher pressure, the jet needs to be sped up considerably to keep from removing too much of the good concrete. At a relatively lower pressure, it is not getting out the bad, or at a higher pressure, what it's doing is it's taking out too much of the good concrete. It's just a lot harder to control and get selective type removal when you're using very high pressure. So this is referred to as ultra-high pressure blasting or hydromilling. It's more suited for deep cutting or non-selective removal type cuts. So selective removal cutting will cut through mortar and around the aggregate. It's not going to cut through rock. Higher pressure machines, though, may actually cut through rock. So on the left, this is more of what I'd consider your true selective removal hydrodemolition type equipment. And it's important to know this when you're out on the job and the contractor brings his equipment out to do that job. So the other thing that's important to understand is that the amount of water flow is the means of production and profiling for the equipment. So more water that you're running through the system means faster production for the equipment. It also means more erosive action or carving out of that mortar line. So if you have a machine producing 60 plus gallons of water per minute with a selective cut, you can probably cover upwards to about 85, 90 square yards per hour in production rate. or possibly more, you know, if you're cutting at a traditional, say, 1/2-inch fast track cut. Whereas if you're using ultra high pressure blasting equipment or other lower water volume producing equipment with, you know, with smaller volume pumping systems, they'll often use much less water, but it also means the production is going to be slower depending on the cutting depth. So the key thing to remember in this is, and if you remember nothing else today, selective removal is a function of pressure and the production rate is a function of the water usage. So the more water you can run through the system, the more erosion of the surface you get. That means more amplitude or difference between your peaks and valleys, and that ultimately means more surface area for bonding. So true hydrodemolition equipment for selective removal of concrete is done most efficiently with high volume water delivery units that use a comparably lower pressure as opposed to a lower volume water consumption unit that would use much higher pressures. So that's kind of the difference in the equipment there. So that was kind of a lot of detail there. Now, I want to walk you through the fast track process, but I want to do this by walking through your specification kind of side by side with it. And I'll break this down by your heading per your specifications. So up front, the North Carolina spec identifies a description of the process, a few definitions, and goes into the equipment. I'll just talk to the equipment here. The process and definitions are fairly straightforward, I think. Now, and so this comes from your spec, and a couple bullets there. The equipment must be able to achieve 17,000 PSI. Although in the field, you may not need that output because remember, it's based on the calibration and concrete quality where you get that pressure range established. The operator needs to be able to fully control the machine, obviously. You're going to use potable water source. Also very important here, this is good in your spec, in conducting like the secondary work you do for cleanup, specify 7,500 PSI minimum pressure. The reason that is important is at 7,500 PSI water pressure, that is what you'd consider the equivalent to abrasive blasting. So that's why you want to make sure if they're using high pressure water cleaning devices that they are in this range, because if they're using regular pressure washers like you might get from Lowe's or someplace like that at 3,000 PSI, those are not acceptable units out there. You need something that's going to be able to deliver 7,500 PSI. And then there's a requirement for vacuum collection of the residual water and debris. So very good in the specification there. So the next section gets into management and disposal of concrete grinding residuals for both the hydrodemolition process and also the texturing operation you're going to do afterwards. Water control, wastewater collection all falls on the contractor. He needs to submit his plan for performing this task. And the idea is that the contractor needs to show how he can control, collect, and legally dispose of the wastewater and slurry. So this needs to be done in compliance with Federal Clean Water Act and also any other state, local agency regulations. So North Carolina has an outstanding spec here with regard to how this gets handled on site. I wish other states had something similar to this, or at least key parts of it like you guys do. I love the checklist that you have. You have guidelines the contractor is required to follow, disposal. You could cover every part of it, I think. I think it's all very good. I can't really add much to it. The big things you're looking at with regard to wastewater is reducing suspended solids and adjusting the pH of the water. That's the real keys that you're trying to handle with wastewater management here. So I did throw a few slides out here just to kind of show you some different things we see in the industry, although most of these are going to be from other states. Although the first one I have up here on the screen is from a job in Wilmington, so it is off a DOT job there. Looks like the water's being channeled to the end of the bridge, which is typical. Pea gravel dam to help. What that does is help slow the velocity down, allows some of the suspended solids to be dropped out. Then it looks like it's flowing through that pea gravel dam and then down to an area where it looks like a pumping system has been set up to pump it to another tank or another location there. So I'll go through a few slides here, just so you can kind of see how it's being done in different states. Another job here has check dams. This is pretty typical. You'll see a series of check dams set up like this. Generally, they're going to be on an angle, and you get the water to slow down, trap within that containment area. It kind of gets to a level where it flows, slows down, then kind of flows around the end of that little dam there and down to the next device. You'll do that for a series of devices. So a lot of the slurry can get trapped in there. And then once it goes through the series of those check dams, it's going to collect at a common point. Generally, it's going to be right off the bridge end is where you're going to try to make that collection. This particular job, and this may be similar to what you see on a lot of your jobs, I'm not sure. Looks like they're using a rain for rent tank. Generally, these are going to be 21,000 gallon tanks, and that's where the water is pumped and stored. You can get further settling of material. Plus, it's a place now where you can check the pH. So normally what you're going to find with hydro cutting, that the pH is going to jump considerably. It's going to generally be up around 11, 11.5. If it gets to 12.5, it's considered a hazardous waste, and then that becomes another level of disposal. So you really want to watch that and be careful for that. There are a variety of chemicals that can be used to lower the pH. It's kind of like balancing the swimming pool. You know, you need to find something to lower the pH. So in this particular case, looks like they're using a citric acid that they're mixing into a solution form. You could inject nitrogen. Seen that done a lot, especially on bigger jobs. You know, muriatic acid. There's other chemicals out there. You just need something that's going to be able to help you lower that pH level back to an acceptable range. Here you see a person. He's mixed up some citric acid with water, and he's got a solution there that he's just adding into the tank directly. Then he'll let that circulate for a while, and they'll retest it to check the level. This particular job here, I believe, is in Virginia. An area was built at the bridge corner, fairly substantial area they built here. This is a pretty big bridge, but that's where the water's being collected. They're going to pump it into a series of weird tanks for filtering out the sediment. So they'll pump it into a tank, they'll let it settle in there, and they'll pump it over to another tank to do more treatment of the water. So I believe on this job, this was ultimately loaded. The water was loaded into tankers then after they adjusted for the pH and sent it actually off to a treatment facility. Also on big jobs, you can recycle the water. I don't see it done a lot out there, but for big jobs, it may be worthwhile for the contractor to look at recycling type options so he can kind of limit the amount of water that he's having to haul out to the site and the amount of water he's having to handle for treatment. Here in this particular bridge, this is out in Missouri, actually water is just being funneled directly down from the deck, and the contractor has a tank below the bridge. So he's got some check dams up on top, kind of getting as much of the solids out as he can. Then he's just letting it free flow down into the tank below and treating it down there and moving it from there. So that's a little bit about water control. Move on here to overlay surface preparation. And this is what the OSP plan boils down to. It's the contractor's proposal of his equipment and means to accomplish the work. So this includes how he's going to estimate the depth of the reinforcement steel in the deck, and then what type of scarification equipment will be used and how the removal will occur to achieve the desired cutting depth. Also how he will verify that he has, in fact, cut to the required depth. And then the same thing with his hydrodemolition equipment. What kind of equipment will he bring out? How will he achieve the depth of removal with that equipment? So that gets us to the main event here, that actual surface preparation work that is to be done. And for Hydra demolition operations, there are two reasons that milling is required. One, you have to remove all overlay material. You have to get to the base original concrete in your deck. You don't want to try and remove overlay material via Hydra demolition only. Overlays that you have out there, such as latex, low slump, anything dense, they're going to be much too dense for you to be able to cut into those. It's going to be very difficult to remove those with Hydra demolition equipment only. Also, once you do get to that base deck, you need to get into the original deck now. Generally about a ½ inch or so. That helps to open it up, and that's real critical. If you don't mill that surface and try to hydro into a smoother type surface like the top of a bridge deck, the initial reaction will be that jet is going to want to try to bounce off that deck initially and not begin its cutting process. So it's important that you get it opened up to allow the jet to gain that bite that it needs to start that cut. So bottom line, mill for depth as much of the material as you can, or as much as you need to, because that's going to be the quickest and most cost-effective means for the contractor to get the material out. And that's why milling is preferred and done up front. And then the entire removal is not all Hydra demolition either. So that facilitates the process so much more when you do that milling, and then let the Hydra demolition do your surface profiling and selective removal, which is really what you want it to do. So the North Carolina DOT spec covers this pretty well in the specification as far as scarification. It calls for removal of material to the original deck and then down into the deck per the plan limits. And it even goes further. Don't get closer than a ½ inch into your top mat of steel, and it even gives guidance to the contractor for checking that steel out on the deck, or that depth of steel. So I think that's real good spec there that you have. When you are out on these decks, you really want equipment that is good and compact, probably 25 tons or less as far as milling equipment. You don't want those big asphalt pavement milling machines out there. They're just too heavy. They can cause further damage to your deck. Plus, the contractor needs to have the right cutting teeth on his mill. And it may even require him to make several passes to gain the desired depth in a uniform manner, and to make sure that that reinforcing steel is not being contacted. So it's nice to have equipment that can get close to the rails, the joints, mill out as much as he can. What that does is it just kind of limits the handwork that then might have to be done by the contractor at those tighter areas. So the finer that he can cut that with a mill just creates less handwork for the contractor. This is your typical milled surface in the field. That mill's going to cut through everything, aggregates included. So it's cutting across the tips of the coarse aggregates. Bottom line, this is what you want: good, uniformly milled surface, 100%. Don't leave any what I would call bald or high spots in the deck. So that leads us to the calibration process, and it's to be done in 2 distinct locations as outlined in your spec. Areas approximately 50 square foot into sound concrete first, and then move over to an area of perceived unsound concrete and perform a second calibration in a similar size area. Now, with that initial calibration into sound concrete, the cutting depth is established, but also the texture or roughness that the jet is achieving. Both of those are going to be important to you. Often the specs will require an initial calibration to a specified depth. Generally a ½ inch is common, and I think that works best. Sometimes you'll see a ¼ inch, but I think that's a little light, and the selectivity is achieved a little bit better when you can get that good ½ inch cut. So with the calibration, there are several parameters that are being set. One is the speed of the cutting jet and how fast it'll track or glide transversely on that track. Then also, of course, the amount of pressure that the jet will cut with, the amount of water it's going to be used, the step of the machine, Any information on the water jet itself, say what kind of jet, the size of the orifice, what's the distance of the jet from the concrete surface. So there's various parameters there. And this picture just kind of shows you the back of the machine where that high pressure water is routed in, and just a good view to see where that jet will be sliding on that track back and forth. Now, one important note I want to make about the depth of cut. When we call out a cutting depth with selective type removal, it's not going to be a clear cut depth to the top of rock. It's an average cut to the mortar line. That's what you're going to be looking for. The reason is, like I said earlier, with selective cut hydrodemolition, you cannot cut through the rock. You can only cut around it until you can unseat it. So if you're using a 1/2 inch cut, for instance, you are looking for that average depth of the mortar line to be cut out about a 1/2 inch. So you'll have some areas higher, some will be lower, but on average you should be getting a decent 1/2 inch of removal across that surface if that's what your specification is. So I wanted to illustrate that in this particular drawing here as far as what's happening. So say this is your milled surface kind of on the left there where you see the kind of the squiggly lines there. And I want you to watch when we hydro it. So kind of keep your eye on the rocks in particular, kind of on the left side there as I go to the next slide. You kind of notice how the aggregate is generally left in place and the mortar line is being cut out. I'll run that back and forth a few times there. You can kind of get a better eye on it. So you're cutting around that rock, except where you have the delaminated or weakened concrete there. It's going to actually remove that material then, which is what you want. So that's what would come out. So kind of gives you an idea of what is actually happening theoretically with the material as the cut's being made. Also had a plan drawing here. I think I got this off a job in Delaware. They put this right in the plans, which I thought was pretty good. It's hard to read here, but hopefully it gives you an idea. It just kind of shows that the average cutting depth. They actually call it out on the plans, and they'll call out the amplitude expected. So with a 1/2 inch cut, if you're getting that 1/2 inch average, you're looking at an amplitude range of about 1 inch, which would make sense. And then getting back to the actual field, calibration here, you can see after calibrating on sound concrete, you're going to move to that area of unsound concrete that you've perceived out there and run with the same settings as you did in calibration 1. And then this verifies that the machine will selectively remove all that unsound concrete. So very important, you get these 2 calibrations set up initially. You want to clean up that second area, check it out thoroughly. Did you in fact get the selective removal of that bad concrete out of there the way you want it? And also, are you getting that good roughened texture that you desire? So if it doesn't satisfactorily provide this, you have to kind of readjust, do a little more calibration. And your DOT spec does go into this and says, if you don't get that cut the way you want it, it says go ahead and take an additional 1/4 inch cut into your sound concrete. So when the 2 calibrations are deemed successful, then you record your settings and you're ready to go ahead with the production of the deck then. So the hydrodemolition operation is now ready. This spec in North Carolina also gives information on how to handle and treat exposed rebar. Makes reference to your class 2, class 3 patching, also when to repair reinforcing steel, among some other things in here. It is going to be a total surface operation process, though. We're going to start at one end of the deck, run the entire surface area of the deck. You don't need to sound or mark out the deck area, but the robot's going to find all those deck delaminations for you. Cutting width on these machines can vary out there. I think commonly you'll find they're about 8 foot for most of them, although they can adjust the gate settings to cut narrower if necessary. Normally I'd run a video in here showing the operation with the robot, but I'm finding with these team meetings they're they're pretty choppy and not very clear. So I'm just going to jump over here to the photo here. You can kind of see the debris trail that's left. Where you do have traffic as an issue, it may be necessary to install some other protective screening to protect it against protect your traffic against any flying debris that might come out of the base of that robot. Just kind of be aware of that one. And then another look after the cutting's done, what you have is your debris left on the deck, and that needs to get collected now. That's where we're at. We're with the cleanup process. Need to get all that rubble picked up, but also important is to get all the slurry cleaned up before it can dry on the deck and the steel. That's going to include cleaning and washing the surface. As part of that, there's protecting the exposed steel and not damaging it during the vacuum collection process, and how to handle any additional removals that might be necessary after the hydrodemolition cleaning process is completed. So for these fast track operations, a vac truck can often drive directly on the deck and suck up all the wet debris and water in a single operation, provided there's not too much exposed unsupported steel there. But a vacuum type collection system is what's required per the specification. So you kind of notice this, we'll call a shoe that's collecting the wet debris and water. You can kind of see behind the shoe how it's cleaning up the deck. For this particular picture, the truck would be moving from right to left across the screen. Kind of hard to see, but if you look real close, you can see the cleaned area of the deck just between the shoe and the wheel. And as it's vacuuming, it's also got high pressure water on the bottom there that's able to kind of wash simultaneously to help with the collection process. Here you can see the vehicle has cleaned a section near the barrier, still needs cleaning, obviously, and you can see the difference from the passes made. So it's going to take multiple passes in order to accomplish the cleanup satisfactorily. But finally, when the deck's cleaned up, you should be able to notice the profile. Here you can get a good feel for the roughness, the randomness in that cut that's been made. And the final part of your spec is the measurement and payment portion. And really, that's pretty straightforward. Scarification, hydrodemolition, pay items, each separate, each paid per square yard, regardless of the depth, which makes it real convenient. Easy to determine that based on planned quantities, and really no reason to overrun unless there's going to be change in scope or something out there. That gets us through the spec overview. So I want to touch next on general observations with regard to hydrodemolition, how to evaluate it in the field. There are some things to look for out there, and I've kind of put together just a kind of variety of pictures here. Ideally, what you want to see is very roughened surface that has good amplitude between the peaks and valleys. If it's a 1/2 inch cutting depth, you're going to find about that 1 inch variance in the peaks and valleys within the cut. You also want it to be random, lots of available surface area for bonding purposes. You don't want distinct patterns of jet cutting visible. Great irregularity in sound surface. That's what you're looking for. This is my favorite picture when I refer to selective removal. It's picture definition. I think it shows. You can see the variations in the cutting depth, the randomness in the cut. The rebar exposure is classic of the selective removal that you should get with the proper jet calibration. You can obviously see where the bad concrete was, yet you still have a lot of areas of good sound concrete that have been left in place, and they're roughened nicely for us. So this all gets poured back in one monolithic pour. You don't have to go in and do any interim pours with the exposed areas. You're just going to make one monolithic pour and pour in all those variations in with the overlay pour. Now, note all the exposed rebar from this operation. The rebar is an obvious place where that deterioration is going to initiate due to corrosion, but it's often just that line and above where you run into a lot of deterioration and delamination there. As long as you can catch it fairly early in the deterioration process, sometimes they get too far gone and you have a lot more problems. What I wanted to kind of point out here was, though, this is a closer look at that previous slide. And this may be a little contrary to how you handle this situation in the field. Not sure how North Carolina is handling this, but we typically recommend that for these fast tracking type jobs where you're using latex concrete, you can waive rebar clearance requirements around the rebar, provided you have concrete that is surrounding the bar that is still sound, and there's no obvious debonding of that steel from the concrete interface. So what we don't actually want you to try to chip this, because when you do that, you're just defeating the purpose of the Hydra demolition, and you're also risking doing further damage to the deck or the reinforcing steel. What I'm showing you here, this is what I'd classify as improper milling. It looks like maybe some asphalt or old overlay material is still left behind because the deck just did not get milled deep enough. The problem with this is that you cannot calibrate your water jet correctly with this surface, or it's going to be an area that if you have calibrated it, when the jet hits this, it's going to want to bounce off that differently when it hits this particular smoother area. So it's real important that you're getting that good 100% coverage with that mill, so you can get that bite down into the deck and allow the jet to open it up. So if you calibrate in a nice milled area, when your jet hits that, like in this deck, there's going to be a noticeable lack of cut into that deck. It's not going to be what you really desire to have out there. So take a look at this one here. Notice that the diamond type texture in the deck surface there, kind of, especially in the foreground, you can see that. Tells me the cutting speed here was probably too fast and the calibration was probably not correct. Could have also been some lack of milling depth in there possibly, but you want a much more roughened and random outline when you're finished. So another issue, and this is the same deck as that previous slide, look at the pile of debris from the jackhammering. This was all after the Hydra demolition. So again, the calibration is wrong here. There's no way you should have this much hand chipping. So just a poor job of calibrating. They just went too fast. Just impress upon you, you need to take extra time, really zero in on that calibration, because it is critical. And make sure you get the good sound concrete calibrated first, and then obviously that helps you establish that baseline, and then check it in that second calibration. Now, this particular deck here looks like it's cleaned up, not real deep or random. It's kind of a nubby appearance, I'd call it. It's almost kind of smooth even. You don't have the noticeable peaks and valleys and the angular type pieces in it. The lack of erosional depth kind of tells me it's likely that this was done with a low volume pump. So the rapid erosion was just not there to get the good profiling for the speed of cut that was used. That's why you don't see, that's why you don't see that good irregular texturing here, is because of the equipment that they used here. This one I classify as the worst hydro deck I ever seen. Notice the areas where that rebar is exposed, and the contrast in the texture between that area and the area where you kind of see the other nubby areas in there. What's happened here is they've gone in and they've hand chipped in all those areas where that rebar is exposed, because the delaminations were left in place. So yeah, you really want to minimize your hand chipping, because the other thing hand chipping does is it clips off the peaks of your aggregate as well. So you lose your texture in addition to, it's just not a very, very good cut there. So I suspect maybe the deck was a fairly thin deck, and they were just afraid of blowing through possibly. So they might have went really fast and just they thought they were going to be able to cut it okay, but really just kind of a waste of Hydra demolition here. They're not going to get much life out of this overlay, I wouldn't think. There's nothing to grab to there. They don't have any mechanical grip in there to be able to grab with. Here you have a cut. Again, this actually was a 1/4 inch cut. They got some decent depth there. a little bit of pattern cutting in it, but that's what you're going to see with those 1/4-inch cuts, I think. So because you're running at a little higher speed, so not quite as random as you want. And that's why that your 1/2 inch gives you a little bit better randomness in your cutting. What happened on this deck? This was actually a voided tube structure, so I know the contractor was really concerned about blowing through those void tubes in his deck, so that's why they went with a fast cut there. But one thing I wanted to point out about this particular photo, the longitudinal crack you're seeing there. Look for that structural cracking in the deck and document that. When you have structural cracking out there like this, there's a good chance it's going to reflect back through your overlay at some point in time. So it's just good to kind of be aware of that. Existing patches in your deck are acceptable, provided that they're sound. You also want to see a little profiling in them too. You're likely going to notice a little bit different cut though when the jet does hit these patches out there, because you're not calibrating on the patch material. So don't be alarmed by that if you don't get the same cutting texture that you're desiring on those. But you are getting the good selective removal here too. It appears in the photo. So again, best off not to touch those bars. The LMC will adhere, fill around that very nicely. You get good chemical adhesion with the latex concrete, which makes it work very well in conjunction with the mechanical grab that the Hydra will allow for. Just want to point out here, you see the rebar exposure. It's not due to selective removal, but rather in this case, it just happens to be machine overlap where the robot was, when they went to the adjacent side, they just went over too far and cut a second pass in an area. So that's what caused that rebar to expose like that. This looks like more patches. They're being undercut, delaminated in place. Not uncommon to see that with hydrodemolition. As that jet hits the patch, it's going to start to grab it, but it's going to probably be moving too fast to rip it out entirely, since you're not calibrating on it. If that material has a certain strength, it's going to resist the water jet. So patches, after hydroing, you're going to want to sound them, verify that they can be left in place. Parts of them may have to be chipped out. If some agencies like to actually remove all the patches from within their deck when they're out there working on it. A few notes about deck condition. You may be thinking, what about jet blow through? You can get an idea of the potential for blow through when you look under the deck. Here, for instance, just some cracks with efflorescence, not likely going to be an issue. Even this, you have some minor saturation, pretty good from underneath, gives you a good sense where you may possibly have a localized pop through. But with the speed of the selective cut, that's another advantage of it. It's probably going to bridge pretty well. So, if anything, maybe just a very small hole might develop there. Something like this, though, very saturated, really a full depth repair. If you do have areas of known full depth, I always think it's best to try and do those ahead of the hydrodemolition operation. That way you're not trying to handle all the water and debris from the blow through, because that creates a lot of extra work for the contractor to have to try to set all that up, that containment underneath the deck a lot of times. So small punctures you can handle pretty easily on site, but when it gets to be large areas like that are going to be full depth, it's usually a lot easier for him to handle that up front before he does the hydro. Underside false decking might be necessary, especially if you're over traffic or streams and you suspect that you could have the potential for some of those blowouts to take place. Got several things going on here in this particular photo. One, it looks like the inspector actually noted some areas where the bar was unbonded or delaminated concrete remains. So these areas that are going to need a little hand work. Looks like he painted kind of those areas out in the field. You may notice towards the bottom left, some rebar with epoxy stripped off. If you do have epoxy coating on your bars, that will likely be removed with the process. Most agencies at this point don't try to repair that in the field. You also need to be aware of the rebar section loss. Generally, if you find bars with 20 to 25% loss of section or more, you try to splice in new bars. You also see up in the top right, looks like there's a hole punctured through the deck there, a few little holes. Those you're going to go ahead and sound, mark out, cut out, do your traditional full depth repair in there. Normally when you patch, you'd pour the repair material back up to at least half the depth of the slab and leave it just under the top mat, and then pour the rest with the overlay material. And North Carolina spec may differ a little on that, I'm not sure, but that's kind of traditionally what we'd see. When you do hydro, the jet will clean up the steel pretty well, I think you'll find. However, as that exposed deck steel, sits out there for an extended period of time, you're going to likely find rust bloom. Minor rust bloom's okay, but heavier rusting like this does need to be cleaned up, and that's why, as that last order of business, the contractor's going to need to go in with this one last thorough blasting operation prior to the overlay installation, either abrasive or the 7,500 plus PSI water blasting. Okay, that kind of gets me through it. Hopefully you found some of this helpful, and maybe a few things you can take away for future jobs. If you would like a PDH for today, please email me at one of these addresses on the screen here. And also I'll mention, if you were on the latex presentation a few weeks ago, I'm still working on PDHs for those. So, but if you were on that and you did not respond and you need a PDH for that one, you can also tell me you need both of them and I can get them completed. So hopefully I'm going to get those done in the next few days. And I can take some questions here if we have some time.
Hey, good morning, Pat. This is Aaron Earwood. Doesn't look like
Yes.
there's any questions. Again, encourage anybody to ask them if possible. But just want to thank you again for presenting this for the second time, and giving those that didn't get an opportunity to listen the first time to see this and listen in. And just to let everybody know, we did record it this time. Is one of the main reasons we did the encore presentation. So we thank you again for that, Pat. We did record the latex modified concrete overlay presentation. And so if you didn't get to see that one, we do have a recording of that we're going to post and make sure that's available for everybody. So I just want to thank you again for the information on both presentations. It was very informative and useful, and hopefully we'll help folks out in the field as they administer these contracts. So thanks again, and thanks everybody for joining.
Okay, thank you, Aaron. I appreciate it. And with that, I guess I'll go ahead and stop our recording, and I'll get this copy to you as soon as I can here.
Thanks again, Pat. Good job as usual.